Now I introduce reinforcement learning. Reinforcement learning tries to solve interactions between an agent and his environment by formulating the problem to be a Markov decision process. Markov decision process is a 5-tuple, includes state, action, reward, state transition probability, and the next state. Whereas includes the agent internal information and outside information. For a Markov decision problem, if agent knows the state transition probability, agent can select action, and his environment generates a reward to respond to the agent's action. And then the agent moves from his current state to his next state. However, in the actual problems, an agent doesn't know the state transition probability. So an agent has to learn or understand his environment by learning from human demonstrations or from his own explorations. Once the agent understands or learns his environment, he can find a policy to select an action and receive a reward, move from his current state to next state. An agent needs a sequence of steps from initial to terminal states. So we need to define return reward along a trajectory or episode. Let's say this G is a reward return along a trajectory. First part is incident reward. The rest of them is a future reward. Since the agent is not confident about the future reward, so we need to define discount return by introduce the discount rate to reflect the future reward delay. And then we can rewrite this future discount return as the recursive formulation. Here, as first term is incident return, second term is the future discount return. Since the environment is dynamic, so we cannot only consider return along just a single trajectory. So to find the optimal policy, we need to calculate all the possible trajectories under the policy pi. And then we define two value functions. One is state value function, one is action state value function. This state value function is we at the given state S and the policy pi we are searching for. We calculate the state value function. First, we calculate the future discount return along one trajectory. Then we calculate the expectation of all the return of all the possible trajectories. And so, for example, from this S to the terminal, and this policy, we have many possible trajectories. We need to calculate the future discount return along each trajectory, and we calculate the expectation of the return of along all the trajectories. And similarly, we define action state value function different from state value function is we select action from pi, and then for given state S, we calculate the Q function. Similarly, firstly, we calculate the future discount return along one trajectory. And then now we calculate the expectation of the future discount return along all the trajectories. And also, by find the pi, we can get the maximum state value function, or we can search for pi to find the maximum action state value function. If we use the backup diagram, you will use a circle indicate the state value function, and we use the solid third indicate the state action state value function Q. The relation between the V and Q is through a policy pi. And then from this Q to next state, this depends on what's the state transition probability, and what is the P you select, and you get the corresponding reward, and then that's from the state S to next state S prime. Once we have the state value function and action state value function, and through this backup diagram, we know their relationship through the policy pi is here. And then we can, the problem is how can we find the optimal policy pi? And then we have a Bellman equation. Then we use the Bellman equation by using the neural network to solve for the optimal policy. And this here is the two basic Bellman equations. One is for the state value function, another for the action state value function. Bellman equation just split the reward or the return into two terms. For example, here is the state value function. We calculate the state value function at S, state S and the policy pi. We calculate the expectation of these two terms. First term is the incident reward. The second term is the future discount value function. And similarly, the Bellman equation for the action state value function Q different again from the state value function is we select the action under policy pi for given state S. Under policy pi, we calculate the Q function. Bellman equation divided the return into two terms. This is the reward and this future discount action state value function. Then we calculate the expectation of the two terms. So for AI, right now we use AI to solve reinforcement learning through a deep neural network, solve for the optimal policy. And here, this is just to show if we solve the Bellman equation for state value function, that means we from this state pass this Q function, reach this next state. And for the Bellman equation for action state value function, we start from SQ. SQ is for selected action and the policy pi. And then we are, for given this state, we calculate we use this expectation formulation from this Q at SA to the Q at S prime and A prime. For more details, please check with this reference. Thank you.